G'day, I'm Lee from Platypus Technical. Welcome to part 2 of our series about using a thermistor and a microbit to accurately measure temperature. Platypus Technical is a science and engineering consultancy, so we do research and development, but we also make resources to support science and engineering education. So let me know what you want to learn, and you can do that in the comments or through our Twitter, Facebook or Instagram. So part 1 of this series went through the basics of a thermistor and showed you how we can use it to build a transducer that converts temperature into voltage. The reason we want to do that is because our microbit can't measure temperature directly, but it can measure voltage. So how do we use what we learned in part 1 to make our temperature measurements with the microbit? First, we need to do some electronics engineering. Basically, we need to design and build a circuit that will convert the temperatures that we want to measure into voltages that the microbit can measure. Now I hear you saying, but we already learned about voltage dividers, we just need a voltage divider. And that's correct. We're going to use a voltage divider as our transducer, but there's a little bit of design to make sure that the voltage divider that we use does what we want. So I've decided to measure temperature, but which temperature range do I want to measure? And just as important is what don't I want to measure. Knowing what I don't want to measure can actually save me some time and money. For example, if we try to design a device that measures all temperatures, it can be difficult to make such a device accurate across such a large range, or very, very expensive. At the same time, if the range of temperatures that we choose is too narrow, the device won't do what we want it to do. Now, I've decided I want to measure atmospheric temperature. So this is the air temperature outside, basically the weather temperature. So Platypus Technical is in Canberra. So in summer, Canberra can get as hot as 42, 43 degrees. And in winter, it's commonly -5, but can get as low as -10. So I want to build a digital thermometer that covers that range. So it doesn't matter if I measure things outside this range, but this is the range that I want to be accurate. So now that I know what range I need to use, I can start designing a voltage divider circuit that works within this range. So first I need to select my thermistor and my resistor. If you remember from part 1, we have 3 parts here. We have our power supply, and we have our thermistor, which is going to change resistance with the temperature, and we have a fixed resistor to make the divider circuit work. So the trick here is that if my choosing these resistances and this voltage decides how much current this circuit will draw. Now, I don't want to have extra power supplies in this circuit, so I'm going to power directly from the microbit, if I can, which means 3.3 volts. And that means that the current going through these resistors needs to be low enough that the microbit can supply it itself. Now, if I have a look at the microbit datasheet, which is like the instructions for engineers on how to use a microbit, I find out that a microbit can provide up to 5 milliamps without any trouble, and that's at 3.3 volts. Now, we have an important equation called Ohm's law, which basically says that the voltage in a circuit equals the current multiplied by the resistance. Using simple algebra, I can rearrange that to know that the resistance of the circuit equals the voltage across it divided by the current going through it. So if I put 3.3 and 5 milliamps is 0.005 amps, that's going to give me 660 ohms. Now, we saw in part 1 that as resistance goes up, well, actually this equation shows it, but if resistance increases, the current will decrease because they're on the same side of the equation, as long as voltage doesn't change. So that means as long as my total circuit resistance is above 660, the current being drawn will be below 5 milliamps, and therefore the microbit will be able to supply it. So now I go to my electronics catalog and I have found a thermistor that operates between minus 25 degrees Celsius up to 125 degrees Celsius. This is fine for me because it includes the range I want to measure. It's okay that it goes a bit further. I'm never going to find something that perfectly does this unless I make it myself. What really matters is that it doesn't go too far because that's expensive, and we'll learn in later parts just creates problems with calibration. So this thermistor matches our range, and it has a resistance of 1000 ohms at 25 degrees Celsius. So now I need to choose the fixed component. I'm going to choose it to be the same and just have a resistor of 1000 ohms. Okay, that means our total circuit, if I draw up our new circuit, so powered by our microbit at 3.3 volts, we're going to have a thermistor that is 1000 ohms at 25 degrees C. Sorry, that's not well written. And a resistor of 1000 ohms. This means our total circuit is 2000 ohms at 25 degrees C. Okay, now if we put that back into Ohm's law, we find out that the current is going to be about 1.7 milliamps, which is less than the 5 that we need to be below, so that's fine. The other thing is that we know that this resistance might go up, well, in fact it will go up and down, that's what we want. If it goes up, the circuit resistance will increase, and so the current will go down even further, which is fine. But what's also important is that even as this resistance goes down, the total circuit resistance won't ever be less than 1000 because of this fixed resistor, which means that our total circuit resistance will always be higher than the 660 that we calculated as our safe point. So now we know what our circuit values are going to be. In part 3, we can build this circuit, test it, and then connect it to our microbit to start taking measurements.